All right, so we're diving into the nano world this time. Specifically, we're going to be unpacking nanoparticle sintering.
Really exciting stuff.
Definitely. And trust me, this is not your high school chemistry sintering.
Yeah.
We're talking about manipulating billions of atoms on like crazy small timescales. It's kind of hard to wrap your head around.
It really is. We're basically harnessing the fundamental forces of the universe at the absolute smallest level.
Okay, but before we get ahead of ourselves, let's start with the basics. What exactly is sintering?
So imagine like a bunch of tiny marbles, each one a nanoparticle, right? Now picture those marbles starting to stick to each other, but you haven't melted them or anything.
Okay, so they're not melting together. How does that work?
That's the core of what sintering is. It's how we join these super tiny particles to make a solid material. And the force behind it all, the secret ingredient, is surface tension.
Surface tension. Okay, I've heard of it, but give me a refresher. How does that even work on such a small scale?
Think about how water droplets act on a window. They like to clump up into bigger drops, right?
Yeah, they try to stick together.
Exactly. That's surface tension in action. The droplets are trying to make their surface area as small as possible. Now, shrink that down to the nanoscale, where you have billions of these teeny tiny nanoparticles.
So those nanoparticles are trying to do the same thing, just on a much smaller level.
Exactly. And because they're so small, they have this huge surface area compared to how big they actually are. That means they have a ton of energy, and they're constantly looking for ways to lower that energy by reducing their surface area.
So they're like tiny little balls of energy just bouncing around, looking for a way to calm down, basically.
That's a great way to think about it. They want to calm down and minimize that energy by basically teaming up. But here's where things get really cool. The nanoparticles, they don't just melt into each other, they sort of dot flow together.
What do you mean flow together? How can they flow if they're not melting?
It all happens at the atomic level. Imagine atoms shifting around, almost like a microscopic ballet, all choreographed by surface tension. It's all very precise. And eventually, the particles are essentially welded together.
So wait, are you telling me scientists can actually watch this whole atomic ballet happen?
In a way, yes. We can simulate this movement with these incredibly powerful computers so we can see it happening in action.
That is wild. So we can actually visualize how these atoms are moving around in real time?
It really is like having a super-powered microscope. We can see how these atoms rearrange themselves during the sintering process. And by studying these simulations, researchers have actually identified the key mechanisms that control how those atoms move.
Okay, so how many are there?
6. These mechanisms essentially show us the different paths that atoms can take as they move around.
Paths. So like the atoms have their own little highways to travel on?
Precisely. Think of it like a busy city. Some atoms might be zipping along the expressway while others take the scenic route. And just like in a real city, some of those routes are going to be more efficient than others. It just depends on where they're going.
Okay, so far so good. But what happens if there are, let's say, imperfections within the nanoparticles? You know, like maybe there are some atoms missing or the structure is a little bit off. Are those just like roadblocks on our atomic highways?
That's a great question. And you're right to think of those imperfections as being, well, imperfect. They're called crystallographic defects.
Crystallographic defects, got it. But are they always bad news?
That's where things get really interesting. See, defects aren't always a bad thing. They can actually be surprisingly useful.
Hold on, so you're saying that having a few potholes on our atomic highway actually helps things along?
In a way, yes. Think of those defects as shortcuts or detours. They can speed things up by providing new routes for the atoms to travel on.
So a missing atom here, a shifted layer there, that's not always a bad thing. It's more like, what, opening up a side street for little atomic commuters.
Exactly. And it turns out that smaller nanoparticles, they actually have more of these defects because they're more compact and have higher energy.
So the small nanoparticles, they're more likely to have these shortcuts for the atoms.
Precisely. They're like the bustling city center, full of energy and movement compared to a quiet suburb.
Okay, so we've got these atoms moving around like they're late for a meeting. But now you're telling me that the nanoparticles themselves are changing too. It's like the whole playing field is in constant motion.
It really is quite dynamic. And those vacancies, the spots where atoms are missing those, are key.
So how do the vacancies affect everything?
Think of them like tiny little movers, always creating open spaces for other atoms to jump into.
So it's like a never-ending game of musical chairs, but on an atomic scale.
Exactly. And that process, the atoms hopping around, driven by vacancies, that's what we call lattice diffusion.
Lattice diffusion, got it. So that's like the express lane on our atomic highway, right? And the vacancies are the things that keep that traffic moving smoothly.
That's a great way to think about it. It's amazing how such a tiny thing, like a missing atom, can have such a big impact on the entire process.
It really is. But before we get too deep into the weeds here, can you remind me why any of this even matters? We're talking about things happening on such a small scale. How does it translate to, the real world?
It's a good question, and the answer is that it's because we understand these tiny atomic level processes that we can do such incredible things with nanomaterials.
Okay, I'm listening.
For example, let's say you're building a flexible circuit for a wearable device.
Mm-hmm.
You need all those nanoparticles in the circuit to be perfectly sintered together.
Right, otherwise it won't work.
Exactly. And to make sure it works, we need to understand how those atoms are going to behave, how they're going to move and interact, so we can create a continuous path for the electricity to flow.
So it's like we're building a perfectly smooth road. And those atomic interactions are the asphalt that holds everything together.
That is a great analogy, and the better we get at understanding how those tiny atoms behave, the better we'll be at building those roads, and that's the key to nanomanufacturing.
It's like having the blueprints to build anything we can possibly imagine, but on a completely different scale. But hold on, we're getting ahead of ourselves here.
I know, it's exciting stuff.
So, to sum things up, we've got our atoms acting like tiny commuters, our nanoparticles behaving like overeager dancers, and these crystal structures that can, twist and turn.
We've covered a lot of ground today.
We have, but we're not done yet. Next time, we're going even deeper into the nanoworld to see how the size of those nanoparticles can impact sintering. Get ready for tilt and twist. Last time, we talked about how atoms move around during sintering, but I guess I was picturing all atoms as, the same. But what about the nanoparticles themselves? Does the size of the nanoparticle matter?
Oh, absolutely. It makes a huge difference.
So it's not a one-size-fits-all kind of deal.
Not at all. Think of it like sand versus gravel. They're both, similar materials, but they act totally different.
Right, sand's going to be a lot smoother flowing than gravel.
Exactly. And the same idea applies at the nanoscale. The size of a nanoparticle really changes its properties and how it interacts when it comes to sintering.
Okay, that makes sense. So we've got these nanoparticles, and they're not just static, right? They've got energy, they're moving around, bumping into each other.
It's a very dynamic environment.
So smaller particles, they're going to have more energy, right? Because they have more surface area compared to their volume.
You got it. Think of those smaller particles like the really energetic ones in a mosh pit. Always moving, always jostling for position.
Huh. I like that analogy. Okay, so smaller particles are more energetic. What does that mean for how they sinter?
Well, remember that surface tension we talked about? Smaller particles have a much stronger drive to reduce that surface area. They're raring to go, ready to pair up and minimize that energy however they can.
So they're like the overeager dancers in the mosh pit, just waiting for any opportunity to link up.
Precisely. But how does that actually play out at the atomic level? We can't exactly watch it happen in real time. Or can we?
Wait, are you serious? We can actually see how individual atoms move during sintering.
We can. With these really amazing computer simulations, it's possible to track the paths of individual atoms as they move.
That is incredible. So we can basically create a map of each atom's journey as it moves through the material.
Exactly. It's like giving each one a little breadcrumb trail so we can see exactly where it went and how it got there.
That is so cool. What have we learned from these atomic breadcrumb trails? Anything surprising?
Actually, yeah. One of the more surprising findings was that when you have two nanoparticles of different sizes sintering together, the atoms from the smaller particle, they're actually more active.
Wait, really? The smaller particles are doing more of the work?
Exactly. They contribute more to forming the neck, the connection that forms between the particles.
Those little overachievers. So it's not just about size, is it?
No, it's not. Turns out the orientation of the nanoparticles matters too. Think about trying to fit two Lego bricks together.
It's way easier if they're lined up the right way.
Precisely. And just like those Legos, nanoparticles have a preferred way of lining up, or more accurately, misaligning, during sintering.
Misaligning, what does that mean?
It's called misorientation, basically, how the nanoparticles are oriented relative to each other, and it has a big effect on how well they sinter together.
Okay, so how does this misorientation thing work?
Well, there are two main ways it happens. Tilt and twist.
Tilt and twist? Okay, give me a visual here. I'm having trouble picturing it.
Okay, so imagine you're holding two sheets of graph paper, each one representing a nanoparticle. Tilt is when one sheet is angled relative to the other, kind of like a ramp. Twist, on the other hand, is when one sheet is rotated compared to the other, like you're turning a doorknob.
All right, so I'm picturing tilt and twist. Now, connect that back to sintering for me.
Remember our atomic highways?
Yeah, those are hard to forget.
Right, so those are still the main routes for the atoms to travel. But tilt and twist can make it easier or harder for the atoms to move between particles. Tilt is kind of like a smooth on-ramp merging onto the highway, a nice, easy transition.
And twist.
Twist is more like suddenly slamming on the brakes and making a sharp turn. It's more disruptive.
So to use the traffic analogy, tilt good, twist bad. Is that about right?
You got it. And research has shown just that. Nanoparticles that have what we call a tilted interface, they tend to sinter a lot better than those with a twisted one.
It's amazing how something so small, like the angle of these nanoparticles, can have such a big impact on the whole process.
That's the beauty of nanomanufacturing. It's all about understanding these tiny details because they can completely change the properties of the materials we're making.
So we've been on quite a journey. Atoms, nanoparticles, tilt, twist. It's a lot to keep track of.
It is. But hopefully you're starting to see just how intricate, how complex, how elegant things are at the nanoscale.
I think elegant is a good word for it. It's mind-blowing that all these tiny interactions, all those movements of atoms, how those nanoparticles line up, it ultimately affects how materials work in a way that we experience every day.
Exactly. And that's the really cool thing about nanomanufacturing. We're not just observing these processes anymore, we're learning how to control them.
So we can actually manipulate matter at the most fundamental level.
We can.
Okay, so what does that mean for the future? What kind of incredible new materials could we create if we master this?
The possibilities are, well, almost endless, really.
Like what? Give me some examples.
Well, we've touched on flexible electronics already, right?
Mm-hmm.
Imagine circuits that can bend and stretch, opening up a whole new world of possibilities for wearable technology.
So like clothing that can monitor your health in real time.
Exactly. Or how about solar panels woven right into fabric so your clothes charge as you move?
Okay, now that is straight out of a sci-fi movie. But what about things like batteries, solar cells?
Mm-hmm.
Can nanomanufacturing change those too?
It already is. Just imagine batteries that are smaller, lighter, but can hold way more charge than anything we have now. Or super efficient solar panels that can generate energy even when it's cloudy.
Those are some pretty big imagines. You're saying this tech could actually make that happen.
It's not science fiction anymore. These advancements are within reach, and it's all thanks to this deeper understanding of how nanomanufacturing actually works at the atomic level.
This is huge. It's like a total paradigm shift is how we think about building things. But this goes way beyond gadgets and gizmos, doesn't it? What about medicine? What about the environment?
Absolutely. For example, in medicine, they're already using nanomanufacturing to create targeted drug delivery systems.
So that means delivering medication directly to, like, diseased cells with fewer side effects.
Exactly. And when we think about climate change, imagine using nanomaterials to capture carbon emissions or build way more efficient solar energy systems.
It's amazing to think about. Something so small, the way tiny particles stick together, it could have a huge impact on these massive global challenges. But like you said at the beginning, I feel like we've barely scratched the surface. What else is out there waiting to be discovered?
Oh, so much. We're always developing newer and better ways to see and control things at even smaller and smaller scales. Who knows, maybe someday we'll be talking about picotechnology or even femtotechnology.
I can't even wrap my head around that.
The future of manufacturing is, well, it's in our hands. It's really only limited by our imagination and our willingness to explore.
It's both exhilarating and a little bit daunting, honestly, to think we have the potential to shape the future with this level of precision.
It's true. But that's also what makes it so exciting, you know? Every new discovery, every little breakthrough, it brings us closer to understanding and using the full potential of nanomanufacturing.
Well, I think that's a good place to wrap things up. We've gone from the very basics of sintering all the way to the future of manufacturing. It's been quite a deep dive.
It has. And for everyone listening, if there's one thing to take away from all of this, it's never underestimate the power of the very, very small.
And who knows, maybe one of you listening will be the one to make the next big nanotech breakthrough. Until next time.